All right, we're going to look at how we can get some more information out of measurements other than just the measurement itself by looking at how variables can change. So a variable would be something we can measure that might be higher, lower, bigger, or smaller, depending on what it is that we're actually measuring, the stuff that it is. So like a variable of length could be long, it could be short, it could be measured in centimeters or meters or inches or miles, but we can have different values depending on what we're measuring. Now, those values can actually also change depending on the situation. So, if something like a balloon is being inflated, then its volume is going to increase. And as it deflates, the volume decreases. So, that volume might be some value at some point, some measurement, and it changes as you change the size of the balloon. So, we're going to be looking at how we can show the changes like that with some math and with some measurements. Um, and we tend to use this fun little triangle here that's actually a Greek letter. It's the Greek letter delta. And we use it in science to mean the change in something. All right. So we precede a variable with this delta to say this is a change in something, where the variable is usually represented by a letter, kind of like in algebra, how we might use like an X or a Y. But we tend to try and pick letters that make sense with the measurement, with the type of measurement that they were dealing with. So we tend to use things like M for mass, big old T for temperature. We tend to use X's and Y's for distances that kind of go along with the axes that we're used to in graphs. So usually in a graph, something like this, there and there, we tend to have kind of an X-axis and we have a Y-axis. So if we have horizontal distance, we tend to use an X for that, and vertical distance, we use a Y for that a lot of times, things like that. You'll see other letters used sometimes too. Sometimes a D is used for distance, but typically we try and pick stuff that seems to fit in some way, so it's easily recognizable. It's not always just an X or a Y or something like that. Okay. So if we have a measurement that is changing, not just some standalone number, we can show that by putting this little delta out in front. Okay, so a delta M doesn't just mean that we're dealing with a measurement of mass in, say, grams. We're looking at how that mass is changing. So our mass is either getting to be a larger number of grams or a smaller number of grams. Okay, same with this delta T, this triangle T. So that delta means we have a change in this case, temperature. Okay. So whenever you put a delta in front of a variable like one of these guys, like this X, it means we have a change in that thing. And so in this case, we're using the X to represent distance in meters. So the distance that something is away from something else is changing. Maybe it's getting farther away, maybe it's getting closer, but in either case, there's a change in that measurement. All right. Now, if we want to calculate the change in mass or temperature, distance, whatever measurement we're dealing with, it's pretty easy. We just have to be consistent about the order in which we subtract stuff. And we always do the final newest measurement minus the kind of oldest original initial measurement. So it looks something like this. So if we were looking to calculate the change in mass of something, we might call the newest measurement of mass, or the final mass, this M final. So M for mass, final is, meaning it's the newest, most recent measurement. So this is the final mass. Okay, we can use this little M initial to talk about the initial mass, so what the mass was originally. And then our change in mass is going to be equal to the final mass minus the initial mass. And we always do it in that order, final minus initial. Okay, so this MF minus MI is just a shortened way of saying the final mass minus the initial mass. Either way works fine. This is just sometimes a little bit shorter. And so if you end up using something like this in a bigger equation, a lot of times we'll kind of shorten it up. So either way to write it means the same thing. Okay, we're taking the final measurement minus the initial measurement. Okay, so aside from just being consistent, there is a reason why we do it in this order that we'll kind of see here in a second. So I'll wait until we get to some examples to explain that. So let's go look at some things. Okay, so let's try some out. Okay, so during the pandemic, things have been tough, and sometimes I stress eat, which has caused my mass to change. I've been taking on more mass instead of less mass, which is not the ideal situation. But hey, we all cope in different ways. So at the beginning of the pandemic, my mass was about 63.0 kilograms. Now I'm at about 68.5 kilograms. So we're going to calculate my change in mass. All right. Delta M just means the change in mass. Okay. So out of these two bits of data, the 63 kilograms and the 68.5 kilograms, one of them is going to be the more recent, the final measurement. I'm kind of taking at the end of this. Okay. And one of them is going to be the initial measurement. It's what we took originally and where we're kind of comparing to now. So in this case, what I am now, the 68.5 kilograms, is my final mass, my most recent measurement, 68.5 kilograms. Okay. Whereas I was originally 63.0 kilograms at the beginning. That would be my initial measurement. So that would be 63.0. Whoops, that looks like a 6. 63.0 kilograms is what I started as. Okay, so if I want to know how much my mass changed by, all I have to do is take the final mass minus the initial mass. So I'm going to take 68.5 minus 63.0. So let's write that out here. So there's 68.5 kilograms minus 63.0 kilograms. All right. So if you've got some good mental math or you got a calculator handy, you can just kind of work this one out. So 68.5 minus 63.0 should come out to be about 5.5 kilograms. Okay. Now, back kind of on the topic of the order, why we do it final minus initial. Okay. By getting an answer of positive 5.5 kilograms, that's showing that my mass has increased by that much. Okay, since the final measurement is the most recent, and I'm subtracting from it where we started at, that shows that my final measurement is bigger than my initial measurement. Okay, which means that my measurement increased. It got bigger. It got larger. Okay, I got larger, unfortunately. So this 5.5 kilograms is a positive change. It means it's increasing. Okay, so since this is going to be consistent with whatever kind of change we calculate, if we get a positive number, that's going to indicate, it's going to mean we've got a positive or an increase in our change. And if we get a negative number, that means something is decreasing. It means that something's getting smaller or lesser in that measurement. Okay, so let's take another example and kind of put that idea to use. All right. So I have a black light up on my front desk. It's in my little lamp. And I, a lot of times, will just run it throughout the day. And it gets pretty hot. So last time I measured it at the end of the day, it was about 90 degrees Celsius, which is almost as hot as boiling water in Celsius. So it's pretty hot. And I learned that the hard way because I was like, oh, I wonder how hot it is. And I touched it and it's really hot. And then I measured it with a thermometer like I should have done in the first place. Now, when I went and turned off the light and let it cool down, it got back to around 22 degrees Celsius, which is about room temperature in the Celsius scale. Okay, so we're going to calculate the change in temperature of the black light. So in this case, my final temperature is going to be, again, the newest, most recent measurement. It's going to be the final measurement that we took. And our final measurement here is this 22 degrees Celsius. Okay, this 90 degrees Celsius is what it was originally. Okay, so if I wanted to calculate the change in temperature, my final minus initial would be 22 degrees Celsius minus 90 degrees Celsius. Okay, which again, if you've got I'm going to fix that up a little bit, a good calculator or some good mental math, this should come out to be about 68 degrees Celsius. But more specifically, since we're subtracting by a bigger number, it's going to be negative 68 degrees Celsius. Okay, so that means something. That doesn't mean that our temperature is now negative 68 degrees Celsius and it's just dropped really, really low. It means that our temperature has dropped by that much. It's now decreased by 68 degrees Celsius. Okay, so our change in temperature being negative means that our temperature is dropping. It's getting cooler. Okay, so by being consistent and by always doing the final minus initial, we can get an idea of whether our measurement is changing by getting bigger or smaller, by increasing or decreasing. In this case, it's decreasing by this much. That also means that if you're just told a change in some measurement, like, hey, your change in temperature was 53, that means your temperature has specifically increased by 53 degrees. You don't have to sit around and guess and be like, well, did it get 53 degrees hotter or did it get 53 degrees colder? You know for sure, because of the way that we subtract these, that a positive measurement means that it's getting increased, that it's going up, it's getting hotter in this case. Okay. In this example, in number 2, since our measurement is changing and we get a negative number out of that change, that means your temperature is decreasing, it's going down. So if I just said you have a temperature change of negative whatever, it's decreasing by that much. Okay, let's look at some other examples. Okay, I'm going to skip that one because I think I can probably handle that. Okay, same with that one too. Probably could do that one too. Let's look at number 6. I think this would be a good one. Okay, so I've got this racquetball that I use for just about every example in this class. So I have it up on my front desk, and it rolls off the desk and it falls. Okay, and it goes and it falls, it bounces, it rolls away. So it ends up traveling in 2 directions. Not only does it travel downwards, it also travels outwards. So there's going to be 2 changes in measurement here. One of them is going to be the change in its vertical distance, and one's going to be the change in its horizontal distance. Okay, so if you imagine that the ball is up on my desk originally like this. That's not a very good circle, but maybe I can kind of round it out. Okay. So there's the ball. Now, if I was smart, I'd probably go and actually use a shape to make a perfect circle, but that'll do. Okay, so here's my ball here. So our information tells us it starts about 0.9 meters off the floor. Okay. And it falls by 0.9 meters. Okay. And then it bounces 3 meters away. Okay. So it's going to kind of fall like this. And it's going to bounce and it's going to roll. Something like that. Okay. Where this is the floor here. Okay. So let's start with the vertical distance. So the ball starts by being 0.9 meters off the ground. So I'm going to write this here, 0.9 meters is where this is starting. Okay, and we're calling the floor 0.0 meters. Okay, so since the ball is falling from up here to down here, this 0.9 meters is our initial measurement. So I'm going to call it the YI for the initial vertical distance, the initial Y value. Okay, the ball winds up on the ground. It bounces further away, but if we're only caring about how far up or down it is, let's do this in a different color, and I'm only worrying about this part here. Okay, and actually let me rewrite these in that color so I can kind of better show that. So this would be 0.9 meters. This is 0.0 meters going this way. Okay, so as the ball falls, it starts at 0.9 meters off the ground, and then it falls down and eventually stops at 0.0 meters, which is on the ground. Okay, so if we want to take our initial measurement, which was the 0.9, which is our yi. Okay, and find the change as it reaches the floor, which is 0.0. That would be our yf. Our yf is going to be the first number subtracted by our yi. So this is going to be 0.0 meters minus 0.9 meters. Okay, so if you go and plug that into a calculator, or you might realize 0 minus this 0.9 is just going to be negative 0.9, negative 0.9 meters. Okay, now this is kind of a handy thing that physicists like to take advantage of as much as possible. Okay, the fact that we can kind of set our own sort of starting places to make the math a little bit more convenient for us. Now, if I had decided to measure the distance of the ball, not from the floor, but from, say, the center of the earth, that would make my numbers a lot harder to deal with, because I wouldn't have just a 0 in here to subtract from. I'd have some crazy huge number, something like that. If I tried to figure out the distance it was up off from sea level, that would also make it a huge pain. Okay, so when I have the chance to choose my reference point, I'm going to use that opportunity to make the numbers easier on myself. Now, this isn't cheating either. It kind of sounds like I'm saying, oh, you just pick whatever numbers you want. But this measurement from here to here, okay, the difference from here to here is the important part. Okay, if I had made this 1 meter off of, I don't know, sea level or something like that, and this was 1.9 meters, the difference would still be negative 0.9 meters. Okay, so since the difference is what matters, I get to kind of work the numbers a little bit to make my math easier. Okay, so I'm going to call this floor level 0.0 meters off the ground to make my life easier, my calculations easier. Okay, all that matters is the difference between these, not actually what I start and end at. Okay, same goes for how I go with the horizontal distance. So I could make this real hard on myself and say, well, you know, I'm measuring this from the front of my classroom. So this ball is maybe 6.7 meters from the front of my classroom, or from the front door of my classroom, or from the left side of my desk, something like that. Okay, or I could say, well, I'm just going to start the ball here. Okay, and this is going to be 0.0 meters. Okay, and as the ball moves and winds up somewhere else horizontally, I want to measure how far it is from there. Okay, so in this case, our ball is bouncing 3.0 meters away from its original spot. So so let me scroll down a little bit. 3.0 meters from its starting point there, which is right here. Okay, and again, I'm not cheating it because all I care about is the difference between these two measurements. So if I take my final measurement, which is where the ball bounced to farther away, which is 3.0 meters, 3.0 meters, minus my starting place, which was my 0.0 meters. Oh man, you're gonna have to break out the calculator for this one. Or you can say, hey, 3 minus 0 is still 3. Okay, that's way easier than having to actually do some math with, you know, numbers from, oh, this is the distance that the ball started from, you know, this arbitrary point that I picked. Okay, I might as well pick a point that makes it easier on myself. So our ball moved 3.0 meters. Okay, so the negative on this change in vertical distance here, this delta y, just means that it fell downwards. Okay, and this positive 3.0 meters, it kind of fell outward. It rolled outwards from our starting point. Okay, let's look at one more set of examples that kind of goes along a similar path as this. So let's go down here. We're going to look at number 7. Okay, so let's say I'm going bowling. Okay, a professional bowler can throw the ball at roughly 8.94 meters per second, which is pretty darn fast. Now we're going to look at how fast I can throw the ball and see if I'm doing pretty good, or maybe I'm not quite professional level, or maybe I'm lying about how fast I can throw the ball to make myself look good. Let's find out. So let's see. Okay, xi equals 4.5 meters. Okay, that's from the starting line to the pins, which is, oh, and this is a typo here. Okay, this should be XF. Okay, that's our final position to the pins. Okay, so from the starting line, which is 4.5 meters out, to the pins, which is 22.5 meters out, that's how far the ball goes. And it takes 3 seconds to get there to the pins, starting when I release the ball 1 second after I start moving. So I've got the ball, I start moving. 1 second in, I throw the ball, and by the time we hit 3 seconds, the ball has reached the pins. Okay, and in that time, from 1 to 3 seconds, the ball has gone from 4.5 meters onto the lane of the bowling lane, and it's reached 22.5 meters. Okay, so we're going to calculate two changes. We're going to calculate the change in horizontal distance between these two x values and the change in time, which is coming from these two t values. Okay, so let's start with this right here. So our xf, our final position, is going to be where the ball winds up, which is at the pins. Okay, that's going to be 22.5 meters. Okay. Our xi is going to be our initial position of our ball as it starts to get thrown, which was 4.5 meters. 4.5 meters right there. Okay. So if I take 22.5 meters minus 4.5 meters, that would give me about 18.0 meters. Okay. Now, if I throw the ball, let's do a different color, starting at 1 second and it hits the pins at 3 seconds, well, that 3 seconds is my final time. So that's going to be 3.0 seconds minus my initial time when I let go of the ball at 1.0 seconds. All right. So the difference, the change in that time is going to be 3.0 minus 1.0. Let's do it the same way that I was doing the other ones. Like that. It's going to be 2.0 seconds. Okay. Now, these two measurements on their own can tell me how far the ball went and how long it took the ball to get to that place. But I can actually put those two together. Sometimes we can combine measurements to mean something new. So in this case, I can combine my change in position with my change in time, not just to talk about how far the ball goes or how long it takes to get there, but to say how fast the ball is moving. Okay, in other words, distance per time. So the rate at which the ball moves is going to be this change in horizontal distance, which is delta x, this change in position, okay, divided by this change in time, the delta t. Okay, and you could write it either way like this. You could do the delta x divided by sign and then delta t, or you could do delta x, slash delta t. I like to do it kind of on top of each other like this. Delta, let's do it in the right colors. So we got delta x, and then we've got delta t, like that. Okay, and that'll be equal to the speed of the ball. Okay, how far it moves based on how fast it went. Okay, or how quickly it got there. So if I take my 18.0 meters and divide it by my 2.0 seconds, okay, what I get is 18.0 divided by 2, which comes out to be about 9.0. Okay, and my unit now is meters per second. Okay, this might be kind of familiar if you think of it like miles per hour. Okay, it's about how fast something is going, how far it travels in a certain time. So this ball is going 9.0 meters every second. Okay, now if you compare that to the professional bowler speed at 8.94 meters per second, you can probably tell I'm embellishing this a little bit. I definitely cannot throw the ball this fast, but who knows? Maybe someday I'll be a professional bowler. Not likely, but I can always dream. Okay, but this is another way we can measure changes. Okay, we can put together different variables to mean something different. Okay, to find other measurements, we can kind of calculate a measurement that uses other measurements, if that makes sense. Okay, so we'll be looking at more stuff like this that involves distance and time and things like that as we get further into this unit.